Hi, this is Mark Roth, and this is Mathematics for Social Justice. Today's topic is expected value and the Crackerjack problem. I'll describe a lesson that works very well with students. You can give every student a blank piece of paper and have them, with a pencil, make a rectangle that has 50 squares, 5 rows of 10. And then what they're going to do is take a die and roll it repeatedly until they get a 1 or a 2. Regular 6-sided die. So, for example, they might get a 1 or a 2 on their 3rd row, so they would write a 3. And the next time they might not get a 1 or a 2 till their 5th row. And the next time they might get a 1 or a 2 on their 1st row. So they just continue to collect data like that. They can make this, younger students will learn just from doing this. So suppose they got a 1 or a 2 on their 1st row, they would write a 1. Next time they didn't get a 1 or 2 till their 7th row. The next time on their 2nd row, and so forth. So when they're all done with the row, then they add up all the numbers in the row. So maybe their 1st row turned out to be, for example, 28, for example. And then they would just keep on doing that, and then they would get a final result. Maybe their final result would be 170. Okay, so they would be adding up all 5 totals. So the theoretical amount would be around 150. So 150 is, in the ballpark of 170. Or it might be 130. It might be, it's a good chance it's going to be between say 125 and 175. But the expected value for each row is 3, because on average it takes you 3 rows to roll a 1 or a 2. That's because the probability of rolling a 1 or 2 is 1/3, and the expected value is the reciprocal of that, which is 3. But you don't tell the students that right away. Maybe after they collect their data, you can tell them that, and then you want to try to prove the result. So to calculate that the expected value is 3, when the probability is 1/3, there's 2 ways you can do that I know of, and one is long and one is short. So the shortcut, normally I might do that second, but I think I'll do it first. So the expected value we'll call x. Now, there's one chance in 3 that you finish after your 1st roll. That means you get a 1 or a 2 after your 1st roll. And there's 2 chances in 3 that you don't. So what's the expected value of that? Well, it's going to be 1 more than x. The reason why it's 1 more than x is you've already wasted a roll. This is the situation where you did not get a 1 or a 2 on your 1st roll. You got a 3, 4, 5, or 6. So the expected value now has gone up by 1 because you've wasted a roll where you didn't get a 1 or a 2. So if you basically just solve this for x, you should get 3. So this is 1/3 plus 2/3 x plus 2/3 is equal to x. So combine the 1/3 and the 2/3 and you get 2/3 x plus 1. And then subtract 2/3 from x from both sides. And you get 1/3 x equals 1, and then divide both sides by 1/3, and x equals 3. So that's a quick, easy calculation for finding the expected value is 3. So now we're going to try to do the calculation where the probability is not 1/3, but just in general is p. So we're going to have the expected value x is going to be 1 with probability p plus x plus 1 with probability 1 minus p. This would be x equals p plus, so we're going to get a 1, and we're going to get an x. We're going to get a negative px, and we'll get a negative p. So We can cancel x from both sides, and we can cancel these two, this p and this negative p. So we end up with 0 equals 1 minus px. So px equals 1, and divide both sides by p, and x equals 1 over p. So that's the result we wanted. So when something occurs with probability p, the expected value is 1 over p. So if the probability is 1/2, the expected value will be 2, which is the reciprocal of 1/2. And for example, if the probability is 2/5, the expected value will be 5/2, which is just an average, of course, which is equal to 2.5. Okay, so suppose you're rolling a die but not counting sixes. And you're only counting 1, 2, 3, 4, or 5. And you want to know how many rolls it takes before you roll a 1 or a 2. So the probability of rolling a 1 or a 2 is 2/5 now, because we're not counting sixes. So the expected value then would be the reciprocal of 2/5, which would be 5/2. So on average, you would be rolling a 1 or 2 every 2.5 rolls. So if you did 100 trials, your expected value would be 2.5 times 100, which would be 250, if you found the sum of how many times it took you to roll a 1 or a 2, and you did that 100 times. Okay, so we did a calculation where you try to calculate the expected value. How many rolls would it take to roll a 1 or a 2 when you roll a die? Now, suppose we don't know this particular shortcut. We have to do it a longer way. So we could let x be the expected value again. And there's a 1 chance in 3 that you finish on your first roll. And there's a 2 chance in 3 that you don't. But then there's a 1 chance in 3 that you get a 1 or 2 on your second roll. And then so far this turns out to be 2/9 plus 5/9, so there's still 4/9 of a chance that you didn't get your 1 or 2 on your first or your second roll. But there's a 1 chance in 3 that you get it on your third roll. So if we're looking at the trend we're getting here, we have 1/3 times 1 plus 2/9 times 2 plus 4/27 by 3 plus ... So as we can see, this fraction is getting decreased by a factor of 2/3. So we have 1/3, we're timesing it by 2/3 to get 2/9, we're timesing by 2/3 to get 4/27, etc. Now, to sum this, I have 1/3, but I have 2/9 twice, so I'm going to write it twice. And I have 4/27 3 times, so I'm going to write it 3 times. Etc. And then the next one would be 8/81. Which I'm going to write 4 times. So the expected value is going to be the sum of all this. These are all plus signs. And they all go off to infinity. And each time I'm taking a term and timesing it by 2/3. So there's actually a formula that will compute these infinite sums. And the formula is basically, I'll derive it later. The formula is going to be S equals A divided by 1 minus R, where the first term is A, and R is what we're timesing by. So we're timesing by, here we're timesing by 2/3. Here we're starting with 1/3, here we're starting with 2/9, here we're starting with 4/27. So for this sum here, we're going to have 1/3 over 1 minus 2/3. So that's equal to 1/3 over 1/3, which is equal to 1 whole. So this particular sequence adds up, this particular series adds up to 1 whole. Okay, so for this next sum, your A is going to be 2/9. And we're going to be subtracting 1 minus R, and we're timesing by 2/3 again, which turns out to be 2/9 over 1/3, which turns out to be 6/9 equals 2/3. So this sum is 2/3. Okay, so for the next sum, your A is 4/27. That's this A, and we subtract 1 minus 2/3. So that's equal to 4/27 over 1/3, which is 12/27. And that reduces to 4/9. So we're starting to notice another infinite series, 1 plus 2/3 plus 4/9. So if we make that assumption that this continues, again, we can say your A is 1 whole, and then you have 1 minus, and you're timesing by 2/3. So you're subtracting 2/3 again, which is equal to 1 over 1/3, which is 3. So that finishes the long calculation that the expected value is 3. So at this point, I'd like to derive this formula. So if we have S is equal to A plus A times R plus A times R squared plus ... Let's times both sides of the equation by R. So we get R times S is equal to A times R plus A times R squared plus ... Now, if I subtract RS from S, I get S minus RS equals, and I'm going to be subtracting by canceling. If I do that, I just get A. Now I can factor out an S, so I get S times 1 minus R is equal to A. So if I divide through by 1 minus R, that cancels and I get 1 minus R. So this formula is true, but it's only true when -1 is less than R, which is less than 1. Okay, so now we're going to solve a problem called the Crackerjack Problem, which I first learned from Michael Keynes. And so basically, Crackerjacks, I'm not sure they're still sold, but when I was a boy, they were like caramel-covered popcorn, and they're famous from the song about the ball game, Take Me Out to the Ball Game. But anyway, apparently at one point, the Crackerjack box had a prize for kids in it. And let's assume there was 6 different prizes, and they were all equally distributed among the different boxes that were sold. So the question would be, how many different boxes of Crackerjacks would you have to buy on average, until you would get all 6 prizes? So to solve that, we already know so when the probability of something is P, it takes 1 over P tries on average till you get your successful result. So obviously your first box is going to have your first prize. So it takes you that's just 1. So you expect to get your first prize after 1 box. Starting from scratch, how many additional boxes do you have to buy before you get your second? Well, there's one chance in 6 that you duplicate this first prize. So the probability of getting a new prize would be 5/6. But we know now the expected value is the reciprocal, so that would be 6/5. Okay, so now you have 2 prizes. And starting anew, what's the expected value for getting a third prize? Well, there's 4 chances in 6 that you get a new prize, which reduces to 2/3. So expected value would be 3/2 that you get a third prize. And at that point, there's 1 chance in 2 that your next prize will be new. So that would be a reciprocal of that would be 2. So now you have 4 prizes, and there's only 1 chance in 3 that you get because there's 2 prizes you need, and you've already, so it's 2 chances out of 6 you get a new prize, which reduces to 1/3, and the reciprocal is 3. So now you've gotten 1, 2, 3, 4, 5 prizes. What's the expected value of how many boxes you have to buy before you get your last prize? So the probability of getting the right prize is 1 out of 6. So on average, it takes you 6 rolls to get that prize. So the expected value of how many times you have to buy a box before you get all 6 prizes would be this sum. 6 plus 3 is 9, 11, 12. So it's 12 plus these 2 fractions. So this is 1 1/2, and this is 1 1/5. So changing the decimals, this is 12 plus 1.5 plus 1.2. So that adds up to 14.7. So the expected value for the Crackerjack problem is you would have to buy 14.7 boxes of Crackerjacks on average before you get all 6 prizes.